So let's have a little bit of a primer on weight and mass, and especially if we start talking about atomic weight and atomic mass. So if we're sitting in a physics class, weight and mass mean something very, well, they mean different things. And it might be a discovery or a new learning for some of you, because in everyday life, when we say something's mass, we think, well, the more mass it has, the more weight it has. Or if we think something has more or less weight, we think, okay, well, that relates to its mass. But in physics class, we see that these actually represent two different ideas, albeit related ideas. Mass is a notion of how much of something there is. Or you could say, how hard is it to accelerate or decelerate it? Or you could view it as a measure of an object's inertia. And we typically, at kind of a human scale, might measure mass in terms of grams or kilograms. And what's confusing is, if you go to Europe and you ask someone their weight, they'll often give you their weight in terms of kilograms, even though that is a unit of mass. Now, weight, on the other hand, is it's different than mass. Weight is a force. It's how much the Earth, or whatever planet you happen to be on, is pulling on you. So this right over here is a force. And in the metric system, you measure weight not with grams or kilograms, but with newtons. So really, when you ask someone their weight in Europe, they should give it to you in newtons. If you ask them their mass, what they're telling you is actually their mass. They should say, my mass is, 60 kilograms or 70 kilograms or whatever they might be. And it's a very important difference in physics. If I go from Earth to the moon, my mass does not change. But my weight does change, because the force with which the moon is pulling on me, or that we're pulling on each other, is less than it would be on Earth. In fact, even on the surface of the Earth, if you were to even go to the top of a building, you're just so, it would be very hard to measure it, but you're just slightly further from the center of the Earth, so there's a different gravitational force. Your weight will change ever so slightly, but your mass does not change. You go to deep space and there's very little gravitational influence. You have pretty much or close to zero weight, but you're in deep space, and if there's no planets nearby, but your mass is still going to be whatever your mass happens to be. So that's a primer on mass and weight. Now, with that out of the way, I might confuse you, because as we go into a chemistry context, it starts getting a little bit more muddled again. So let me go to chemistry. And in any science, if people just talk generally about mass or weight, this is what they're talking about. They're talking about a measure of inertia for mass, and they're talking about a force when they're talking about weight. But in chemistry, we start thinking about things on an atomic scale. And you will hear the term atomic mass. And atomic mass is literally a measure of mass. It is measured in atomic mass units. Atomic mass units, which is, and we'll talk in future videos, a very small fraction. One atomic mass unit is a very small fraction of a gram. And it is actually defined using the most common isotope of carbon. It's defined using carbon-12. The current definition is carbon-12. Carbon-12 has a mass of exactly 12 atomic mass units. And so chemists use that as kind of the benchmark to figure out what the atomic mass or the mass of any other atom. And you might say, well, why don't they just do hydrogen, and just say that's one atomic mass unit and all that? And actually, they had started there, or they had been there at an earlier stage, but for a whole set of reasons, carbon-12 as kind of being the benchmark, as having 12 atomic mass units, is what people went with. Now, what is atomic weight then? So atomic weight, let me write this in a different color. See, I'll do it in blue. Atomic weight. So if you draw the same analogy that we did up here, you might say, okay, this must be this must be a force. It should maybe, an atomic weight unit would be a very small fraction of a unit. But it turns out in chemistry, when we talk about atomic weight, we're still measuring in atomic mass units. This is still a mass, atomic mass units. But it's not the mass of just one atom or just one molecule. It's a weighted average across many of how typically what you would see, or the makeup of what you would see on Earth. Well, what do I mean by that? Well, on Earth, there are two. The primary isotope of carbon is carbon-12. Carbon-12, which is defined as having a mass of exactly 12 atomic mass units. But there's also some carbon-14. Carbon-14. And what do these numbers mean, just as a reminder? Well, carbon-12 has 6 protons, and the 6 protons are what make it carbon. And so carbon-14 is also going to have 6 protons. But carbon-12 also has 6 neutrons. 6 neutrons, while carbon-14 has 8 neutrons. And I know what you're already thinking. You're like, well, wait, why don't we just say that a proton or a neutron weighs 1 atomic mass unit? Because it looks like this is 12, and I'm guessing that the mass of this is going to be pretty close to 14. And if you're thinking that way, that's not an unreasonable way to think. In fact, when I'm kind of just working through chemistry, that is how I think about it. But they don't weigh exactly 1 atomic mass unit by this definition. Remember, the electron is ever so small, but it has a very small mass, but it is contributing, or the electrons are contributing something to the mass. And so a proton or a neutron have very close. They're close to 1 atomic mass unit. So let me write this down. So one proton or one neutron, very close to 1 atomic mass unit, but not exactly. But anyway, going back to what atomic weight is right over here, the most common isotope of carbon, remember when we're saying isotopes, we're saying the same element, we have the same number of protons, but we have different number of neutrons. The most common isotope on Earth is carbon-12, but there's also some carbon-14. And so if you were to take a weighted average as found on the Earth of all of the carbon-12 and all of the carbon-14, the weighted average of the atomic masses is the atomic weight. And the atomic weight of carbon, and you'll see this on a periodic table. In fact, I have one right over here. Notice the 6 protons, this is what defines it to be carbon. But then they write 12.011, which is the weighted average of the masses of all of the carbons. Now, it's very close to 12 as opposed to being closer to 14 because most of the carbon on Earth is carbon-12. But then we could write this down. This is the atomic weight. This is the atomic weight of carbon on Earth. So this is 12.011. So typically, if people are telling you, hey, I am talking about the isotope, carbon-12, you can say, okay, if you're talking about a particular atom of carbon-12, you would say, okay, that's going to be 12 atomic mass units. But then if you said, hey, I'm randomly, if I have a big bag of carbon, you could say on average, the weighted average of those carbon atoms, they're going to have an atomic mass or a weighted average atomic mass, which is atomic weight, of 12.011 atomic mass units, AMU. So hopefully this clarified more than it confused. All right. See you in the next video.